welcome. You're attending the first of the MIT Nano seminars, first of the ones that will be coming over and over again for decades to come, I would hope. The first set of seminars we refer to as Perspectives in Nanotechnology, as we want to make sure that as we inaugurate the beginnings of the seminar series, we could ask luminaries from across the world, those who have made significant strides in understanding and defining the field of nanotechnology, to come over and share with us their understanding, their expertise, and indeed to launch us onto the journey that MIT.nano is undertaking, which is beginning of the new era, the new age of nanotechnology that is just upon us. For our very first seminar, we have asked a very special professor to join us from Stanford University, Professor Roger Howe. He's the William Ayre Professor of Engineering at Stanford University, and indeed an expert in his own right in MEMS technology, micro-electromechanical systems technologies, and a variety of other related fields. Now, what Professor Howe has done in his time indeed is remarkable, not just because he has visited and stayed and taught at a series of universities, starting at CMU, where after finishing his PhD degree at Berkeley, he decided to join CMU, only realizing back in the 1980s that CMU did not have as good of a microfab as MIT just opened. So in 1985, he joined MIT and indeed stayed with us in the very early days of what became known as Microsystem Technology Labs, or MTL, seeing it grow from the very beginnings to what it ended up being, an entity that right now supports over 700 users, and indeed who has grown to the point where we needed MIT.nano in order to facilitate the next era of what needs to be developed. From there, he went back to Berkeley, spent time designing yet another nanofab, Berkeley's newest nanofab that opened in 2010. But he left before it opened, only to go to Stanford, and yet again participate in another program that indeed supported the nanofabrication at Stanford and beyond. So his perspectives today will be to give us a chance to understand the beginnings of this nano age and to chart the path forward. Roger, please take over. Thank you.
And thank you to Professor Farnaz Nuri for the idea of getting this seminar series underway, and it's a privilege to be back at MIT. So I would like to focus on something that would distinguish nanotechnology as a huge area. A lot of it would be nanoscience, nanoscale sciences. I'm going to focus more on the engineering and the technology side and start off with a brief history. Some of the people in the room were around in 1959. Some were in diapers in 1959. Most weren't. But actually, nanotechnology goes way back. And you probably, or some of you may be familiar with the story of Richard Feynman. I'm going to give you my take on that. And then to be at MIT in the mid-1980s, there was a lot of nanotechnology going on, and I intersected with some of that. And then at Caltech in January 2000, you have an event that's not a scientific discovery, but a political change in funding. You have a national nanotechnology initiative that is now, whether it started in 2001, it's celebrating its 15th anniversary. And I think in fact, it goes back to around 2000, so it's getting old enough to vote. And that is rare. I'd like to look at lessons learned and what Stanford's been up to, and general comments on shared fabs and how there might be opportunities in the 20s, which are upon us, to really accelerate this translation out of these labs. Rather than, they will translate eventually. We want to make that quicker. And then look at a case study on some strange fabrication that was involved my own group as an example of how labs are being forced to be much more flexible and draw some conclusions. So way back when, I wasn't living far away in Los Angeles. Richard Feynman gave a talk called "There's Plenty of Room at the Bottom" at an American Physical Society meeting. And some people have said, well, this is really the kickoff of nanotechnology. Encouraged scientists, especially physicists, to look at the microscale rather than outer space, because there were many, many things that would be interesting scientifically, and to encourage people, he had a $1,000 prize for a very tiny electric motor, and someone won it who was a Caltech staffer, who was a good machinist and built this by hand as a one-off, won the $1,000, which was a lot of money then. It was probably too easy. His other prize was won in the 80s by Stanford students. It involved putting lots of information, and you needed an STM for that. So actually, I was a grad student. I actually didn't go to Caltech, but I attended one of Feynman's lectures at the invitation of my high school friend who was at Caltech. I was at a school you may have heard of, Harvey Mudd, not far away. Drove over. Feynman's lecture was incredibly entertaining in quantum electrodynamics. I was a physics undergrad. It was sailing a few light years over my head, but I hadn't heard of this until it was dug up later, so it didn't really percolate into the applications. In the 80s, Jeff Lang, Steve Centuri, and I, with students Steve Bart, Teresa Lober, and Marin Maragani, got going with polysilicon surface micromachines. This is a MIT micromotor, and this helped kick off a whole industry. In your pockets, you have polysilicon accelerometers and gyroscopes. And in fact, the word spread, not that there was efficient ways of spreading the word then, but I got an invitation to the MIT Nanotechnology study group, spring of 1986, to talk about this exciting research. As a young professor, you have enthusiastic students and progress, and so I actually, the talk went over like a lead balloon. They were totally underwhelmed. This group was organized by Eric Drexler, who was a staff member, I think, in Space Sciences Lab, and later a PhD student in the Media Lab. But he had launched the group to discuss a vision of a mechanosynthetic molecular nanotechnology, and he had a new book out called Engines of Creation, and you may have seen some of these. This is Ralph Merkel and Eric Drexler in this molecular differential gear that's animated. So it was a total mismatch. In fact, we were just doing the same old stuff that people had done since possibly the Stone Age, chiseling away, removing things, and they were, so who cares? In any case, there's been that disconnect over the years between people who are using lithography and people who are using synthetic techniques. I think there's room for both. In the late 20th century, there's a whole lot going on in nano, long before any initiatives. Cornell had an E-beam facility, and they actually were called the National Nano Fab in the late 70s. Hank Smith, it was the MIT Nanostructures Lab in brand new building 39, and it was separate from the ICL because the techniques were being developed to get below the micron scale and well below that. This was, Hank had helped invent X-ray lithography, later rebranded as extreme ultraviolet lithography. So this is mainstream nano, and again, a long time ago. Later on, or somewhat contemporaneously, there was a discovery of a bunch of synthetic nano structures, whether they were buckyballs, nanotubes, graphene. And it was clear to everybody, including me, who was didn't have access to this technology, that there was something here. It was definitely going to be important. How you would harness this, not so clear. Semiconductor, superlattices for photonics. People were putting quantum dots in, not into organics, but into inorganic materials at the time. And I was kind of reading this as a semi-outsider, but clearly there's something there. In fact, I got involved through a collaboration with Roya Maboudian, who's a surface scientist in chemistry at Berkeley. And this is a problem of micromechanical structures, and it was a problem at MIT. They tend to stick really well together because the surface to volume ratio is high. And what was done was to coat these with self-assembled monolayers of different types. And Roya's later work would be in the microphones in your pocket, allowing them to be in a humid environment and not end up collapsing on each other. So here's an example where technologies at multiple scales are being applied, which I think is important. So what about this initiative in nanotechnology? Well, there's a guy at NSF, Mike Rocco, Neil Lane had been the director of NSF and then went to the White House, and Tom Khalil. This is the mid to late 90s, and they decided that we ought to get some critical mass in this, and how did they do that? Well, they worked really hard setting up workshop after workshop over a period of 3 years to try to build a case that there was an initiative in this new kind of technology with the usual resistance that people hadn't heard of it. People would say, well, why do we need an initiative based on a unit, of nano, 10 to the minus ninth? And in fact, they went and arranged for a WTech study. And I was on one of these in '99 a little later, to turn of the century, that went to Japan and looked at various things. And the conclusion was that the US was lagging. I felt at the time that Europe was doing some outstanding work and more focused work. It's probably true. So what happened? There's a House committee hearing. So this is a run-up to go to the US House of Representatives. And someone asks Richard Smalley, who just recently won the Nobel Prize, and he says we should have a serious national initiative in this area. Okay, that carries a lot of weight, but it wasn't in isolation. There was support built. So some of you are going to be possibly at the NSF. Some of you may be running institutions like MIT in this kind of grassroots rather than top-down. It's a huge amount of work. It requires people that are totally committed. And it was my privilege later to work with Tom Khalil, who was also back in the White House in the Obama administration. So what happened in the end? President Bill Clinton went to Caltech, and he gave a speech. And his speech said a number of things. The one thing that perked up the ears of the people in the audience was that there was $500 million for a major new national nanotechnology initiative. And that was an important event. You had Gordon Moore, some of you may know from Moore's Law, was at the time the chairman emeritus, introducing David Baltimore, and there's President Clinton, and here's President Clinton giving the speech, which you can read. He misremembered Richard Feynman's name, called him Richard Simon, but he did refer to 40 years before there was work in nano at Caltech. So what is interesting, another quote, which I believe was written by Tom Khalil, was that you would have materials 10 times the strength of steel, shrinking the Library of Congress into a tiny device and detecting cancer cells when they're at a very tiny tumor, and so they can be treated. And in fact, this is an interesting statement, that these goals are going to take 20 or more years to achieve. And that's exactly why this is something for the government to fund. This is not private capital. No one has an ROI that stretches decades, right? And so in fact, it is, and this was just at the turn of the century, so it's been a little over 19 years, and it's still going. I will make some comments on that as we go along. Here's the funding profile that you can get at nano.gov, which is for the federal government. Now, there was nanotechnology funding already, and so it was probably a 50% increase on a baseline of around $1 billion, but where you draw the borders has always been kind of difficult. And you can see the benefit of grassroots, because you would have NSF, NIH, DOE, DOD, and even Commerce and a miscellaneous other people from the USDA to NASA and all participating. So the money went into all the agencies and was spread very wide. And so you could say this is a let the thousand flowers bloom strategy, right? Rather than a hyper-focus. Now you notice it increased and then it's kind of stabilized, but it's actually, the program is coherent. In other countries around the world and areas, there was a reaction to Clinton's speech. This is before the dot-com crash. And so there was a feeling that the US was on a roll with the Silicon Valley telecom boom, and that now the US was going to own the next generation of technology. And so whether it was Brussels or Beijing or Tokyo, people said, we got to get our act together. And what did they do? Fund nanotechnology. In this case, this is like an amplification factor, right, to get that kind of funding going. Now, one thing that is not trivial and is the you can't just have a nano thing that's going to go forever, right? You're going to have to resell this, re-envision it every 5 years or so, and this is the efforts of Mike and Stan Williams, formerly HP Labs, and your next speaker, Paul Alivisatos from Berkeley and Lawrence Berkeley, and Chad Merkin at Northwestern. I don't know the third author, but you can see nanotechnology for society, convergence of knowledge, technology, and society. At some point, it gets a little difficult to keep rebranding this, right? But you can certainly work hard and keep things going. Notice this is at the Korea U.S. Nano Forum a few years ago. So this was a kind of an international push, and I'd like to contrast that with New York State, which invested a huge amount of money outside the federal government, and this was at SUNY Albany. They have a silicon fab that was expanded with about $500 million of New York State taxpayer money, attracted Semitech, an industry consortium, and then kept feeding on itself and growing to where the claim was there's around a $20 billion investment in infrastructure in silicon nanoelectronics, giant wafers, fab tools. And so, in fact, the article in the Chronicle of Higher Education, if you build it, they will come, was a reference to the fact that Albany would not be the place that you would necessarily expect to see this, but it is the state capital of New York, and it was a jobs program. It is a major set of capabilities that would be not as open by far as a university, and it's now SUNY Polytechnic. So let me just say, for those that are old enough, the what was it? This superconducting super collider in Texas was around 10 to 15 billion just for high energy physics. And you have this nano initiative going on for 2 decades, spending around 25 billion, a radically different approach. And I think the type of research, we don't need the accelerators that the physicists would use. And ultimately, they concluded that CERN was quite a good location for the Large Hadron Collider, and pulled the plug on the funding after they had built part of it. Coming from California, we have a train out in the rural areas that has no tracks laid, but there's some overpasses, and the new governor is trying to figure out what to do with that. You could make it a kind of park, and I don't know, in Texas, this hole in the ground, what is it being used for? It could be made into a monument for possibly a lesson for future generations, and if we ever get the railroad going in 20 or 30 years, we'll have those overpasses. So here are the kind of projections that this is something to look at. This is market incorporating nanotechnology in billions, and rather, it's not the nanotechnology market. What's the difference? How much do you capture, right, in nano? This is a 25% increase per year, doubling every 3 years. Now, I remember when the MEMS industry was going at maybe 12 to 15%. It's very difficult to sustain if you're doubling at every 7 or 8 years. It means the classes are doubling, the number of schools involved. People are working twice as hard or twice as productive and then continue, and you can't really sustain that. So this, I think, is extremely optimistic. And nanotech in the mainstream 5 years ago, $3 trillion by 2020, doubling every 3 years. $12 trillion. That's a lot of money. In fact, there was a European article estimating the global market is 124 billion in 2024, not 12 trillion. So there's a huge ratio. But this is actually the nanotechnology market, narrowly defined. And it's always been a problem in electronics. This silicon semiconductor is not that important, but without it, you don't have the iPhone, you don't have everything. So I'm balancing this a bit, but it is, this certainly got the attention of people in the capitals of the world. And so where do I come in? Well, like I said, like Vladimir said, I've been in MEMS, inertial sensing, accelerometers, resonators, and that kind of thing, which used nanotechnology as a means to an end, not really building at the nanoscale. And I moved to Stanford, and Stanford was part of a network called NNUN, but I moved in 2005, and there was a recompetition in which Cornell, Stanford, and their collaborators competed against MIT, Berkeley, where I was, and Urbana, I think, were the main schools in 2004. And we lost, so and then I moved, and so I ended up in this National Nanofabrication Infrastructure Network, and ultimately I was the head of the Stanford lab from late 2009 and 2011, was in charge of this whole show. So what did that mean? Well, I got an insight into the very different kinds of nanofabs that were around the country, and I was especially interested in Harvard's relatively new fab as it was growing and what the culture was of the staff and that kind of thing. And there was a recompetition in 2014 where MIT, Stanford, Harvard, and Berkeley teamed up with some schools, and we actually, with Vladimir's help at MIT, we won, and the competition was canceled. It's a long story. But in fact, this is a snapshot from a while ago, but if you look at each of these labs, the NSF is funding it to make it accessible. And yet, of course, if you have a fab, if MIT.nano in 2025, if you look at the user community, of course, most of the users are from MIT. Why? You walk across and you're there. Now, the fact is, in 2025, I think there's going to be a large number of users. You could probably use this color, because isn't that about Harvard crimson, right? I think those people will be writing the T down here, using it, and MIT people will be also using Harvard, because the labs aren't exactly plug compatible. And of course, the companies are involved, and NSF was interested in that. We at Stanford have more companies using the lab. And so what's happened? When we had the recompete, there was a company that had no connection to Stanford. Steve Nassiri was an entrepreneur, actually a graduate of San Jose State, local school not too far from Stanford. He had a great idea. He had a credit card, and so he went in and prototyped it with some Stanford PhDs in our lab. And in fact, that has done really well. If you fly into San Jose, the TDK and VenSense now is on the building. And Cornell had PacBio, which had ups and downs, but was one of the early sequencing, single molecule sequencing, and it is in a process of being acquired by Illumina. So these companies, we once went through all the little companies and tried to make an assessment of what the impact was, but having all these open labs has been a very good thing that, again, has been modeled and adapted to other parts of the world. Now, here's a talk. I see a lot of grad students and postdocs. I'm not the lead. Bruce Clemens is the Stanford director, and the overall director is Oliver Brand at Georgia Tech. And so you have all of these fabs around the country that are funded by the NSF to be open fabs. So they won't say no without a very good reason if you need their services. They have more than 2,000 tools and 67 facilities, though these are the core facilities. And you know the one on the red line, and you know the one probably in upstate New York. And UPenn has an interesting new fab. But there's one that you probably don't know, because I didn't know until I visited Virginia Tech. They have an incredibly strong earth sciences program at Virginia Tech. And their whole fab is oriented toward natural nanomaterials. But the tools don't care if it's natural or your nano material. And they're also linked, and it's very small. What does that say? Well, that is a lab in a remote area of Washington State, and that is called Pacific Northwest National Lab, that many people haven't heard about. They've heard of Lawrence Berkeley National Lab, Brookhaven National Lab. What is this Pacific Northwest National Lab? This is a place where they make nano instruments that are not made by FEI or other companies. These are PhD scientists with unique instruments, and they love to try them out on your PhD. So this whole thing here could be viewed as a PhD accelerator. for you. Now, if you end up collaborating with PNNL and you're going to faculty candidate and there's a PNNL letter rather than all MIT letters, that doesn't hurt either. You may end up being roped into a postdoc or something. So I think actually looking hard, in my case personally, the personal story, I was a Berkeley grad student, and I was frustrated in this 11 mass complex process. A tool went down in Berkeley. My advisor said, oh, call up John Schott at Stanford, because he knew, in those days the internet wasn't quite there. So I called him up and he said, yeah, come on down. And I rode the library bus back and forth for a week, and I saved several months on my PhD because I had a similar enough tool I could adapt the process. So if you got tool problems, you can certainly talk to the management. You can even help in some cases, but you can also maybe do a workaround by FedEx. And I think this is a national resource that is underutilized, and especially at MIT where you have much of everything you could imagine, but it may not all be working, and it may not quite give you the image that you need. So what about shared nanofabs? What's going on at Stanford? Well, here is the building, the Paul G. Allen building that dates back from the 1980s. Well, in 1965, we had an integrated circuit lab. That was the lab I used in the early 80s. In 1980, there was a proposal for a new fab that would be a foundry. It was called the Fast Turnaround Facility for Silicon Chips. So Jim Meindl, who finished his career at Georgia Tech, was a driver for that. And the building was built with industry money, and it moved in, the IC lab was moved over with some new equipment, and I think it was an important milestone, this purpose-built large lab. Berkeley and MIT were working hard to catch up, and did in the next 2 or 3 years. Stanford won that first NNUN with Jim Plummer, and was co-prime, and that injected money, and it changed the culture. It wasn't the IC lab, it was the Stanford NanoFab. NSF would put pressure on Stanford to bring in users from other departments, from other schools, and that changes the culture. Stanford was part of the next network with Yoshio Nishi. There were other nanofabs. Bob Sinclair built one that was SNC, now SNF, in characterization. Cam Moeller was the first director of the Nano Center, that's now SNSF. We renovated the SNF. And then down at the bottom here, sometime in the next decade, around the middle of it, we call it the future fab that I think we're currently wrestling with. So Stanford is a large campus. At MIT, it's nice to be able to walk very short distances, even indoors, especially with the frigid weather you have today. Anyway, it's been, at least it's not raining. In California, we've been drenched. So in any event, if you look at an aerial view, this is the Allen building. Here, the NSF is in here. This Stanford Nano Shared Facility injects another S, making it almost unpronounceable. This is mostly characterization, but some fabrication. And that is run by the Dean of Research. SNF is School of Engineering. There's a School of Earth, Energy, and Environmental Sciences that has too many E's, and they run mass specs and mineral analysis. Because Stanford Geo is big, and they have unusual tools that aren't used by many, but they're used, they tend to lead to important discoveries. So if you pan back and look at the campus, let's see, I think we can see the Oval and Palm Drive, the El Camino, and the hospital and the medical school over here. And what are all these things? Well, this is a map that I think was made by the D School. Some of these are, it says restricted access, some students may use. Open access, all students may use. There are the Product Realization Lab, D School Proto Labs, FedEx, why are they on here? Because they print stuff, right? And sometimes that's useful. The art department's on here. So is it nano? No, it's this complete wild maker culture. The nano thing I showed previously is this corner of campus, But across the street in the medical school, they don't call them shared labs, they call them core labs because of a change of discussion. And Stanford, unlike MIT, doesn't really have fabs. The medical school uses Nano at Stanford, but they have a lot of imaging and other facilities that are very useful. The EE department has set up an open electronics prototyping lab, and SLAC, which is not the social media thing. This is used to be Stanford Linear Accelerator. They have a nanofab for zone plates for X-rays that has an amazing E-beam. So Stanford is not an institute of technology. It is a university, and it's very distributed, and organization is not our strong suit. We have lots of stuff happening, and you'd need a bike and be in pretty good shape to go visit all of this. I think one thing that has been culturally important, this odd logo is the D School. There's 2,000 users. The students or someone pays $100 per academic year to get access to these labs that would go from 3D printing to melting metal and casting things. And PhD students sometimes get benefits, but the focus is undergrads and masters. In Lab 64, we would have complemented the ME-driven D School so that people can embed electronics. So that culture is going on, and then you come into the clean room. People are dressed in white bunny suits. These are the high priests and priestesses of technology, right? There's a barrier there. Some people are attracted to that, to join the priesthood. Other people, I don't want to, how long does it take to get in this thing? You don't like to be in this kind of bunny suit. Why? Because you happen to be a student taking classes and all. But the nanofabs are clean because these are all HEPA filters. This is class 100 because of the nature of the work. But we do weird stuff at Stanford. This is a centimeter thick wafer scale germanium WIMP as a dark matter detector that goes down in a mine. And when I took over, a month later, I got a visit, and this is actually a Berkeley physics student working at Stanford making this thing with a number of people. Blas Cabrera in physics visited me with an entourage of muscular postdocs and grad students crowding into my office. And the discussion was the importance of minority carrier lifetime, both in the abstract and to my personal future, that the lab had to stay clean. Why was he concerned? Because I am the first non-MOS electronics person to be in charge of the lab. He's concerned that the lab will become too flexible. Therefore, there's no Nobel Prize for dark matter detection, and it's a disaster. So, by the way, the centimeter thick wafers, we have special spinners anchored to the floor because these things have mass. And they're trying to scale up to larger diameter wafers. So what does our community look like? Well, Stanford is smaller than MIT. And in fact,
Small in what sense?
in terms of...
Not the student body.
But the students are not all engineering. So I'm thinking from the engineering school, we have 250 faculty total in all of engineering. And MIT EECS is 100 and something, right? 350, okay. All of engineering, 350. So we're somewhat smaller, right? Yeah, we're bigger than Berkeley a little bit in engineering. So these are the eras. Yoshio Nishi, yours truly, and Nick Malash in materials as the new director. You can see the evolving user community, and we've separated the users into ones that almost live in the lab, moderate users, and then these light users. And you can see that there's changes over time. NNIN started there. There was a student revolt at this point, no kidding, with petitions and frustration because of excessive industrial use, running the lab into the ground. You can see these are Stanford users. What's not shown is there was a huge surge in small companies, and the tools were being run into the ground, and the students weren't making any progress. So basically, that had some consequences and improvements in the way things were run and priorities for the local people, and that I took over, and we renovated, and then NNIN ends, And so if you look at what's happened is that we have a drift from silicon electronics and MEMS on silicon to other substrates, materials. People are not doing long process runs a lot of the time. They come into the lab and do a few things, then they go to a private lab or a semi-shared lab. The rate structure capped, so if you spent 100 hours in the month, the last 20 were free. So there's an incentive for groups to send a few students in who would almost live in the lab and do very low-cost fab. That had compliance issues, and we replaced it with a soft cap where we bill a certain amount per hour, and then it drops as you go above a threshold. And that turns out to hurt the super heavy users. What it often meant is that it didn't matter. Now more than one student was going, and some groups would just load up a single student. So in fact, how are we adapting to change? Well, we've launched something called the Exfab, which is fast lithography on even 3D surfaces, not necessarily super high resolution, doing heterogeneous things, trying to embrace in the shared lab 2D transfer processes and building 3D systems. Max Schumacher, also known as Professor Schumacher, would be one of the pioneers in that, doing his research at Stanford. And even things that aren't really the same, like maybe specialized 3D printing rather than garden variety 3D printing, laser cutters, millers, post-machining, all kinds of stuff. See what works, and we managed to sell this. Oh, and yes, lower rates so that it's cheaper for the faculty. So the guy that helped launch this and is the faculty director is John Fan. This is not a graduate student, this is a professor. Okay, we have some professors, it's clear that that's not a student, but not this guy. Anyway, he did his PhD at Harvard CNS. Up the road. He's a Harvard PhD. And he would be doing some pretty radically interesting things in nanophotonics and all. But even more radical would be this guy, who you may not recognize because this is a somewhat older photo. This is the break room, the kitchen outside the SNF. And normally we don't see wafer processing underway in the kitchen. If it's a wafer, it's something edible. In fact, Max is trying to do this carbon nanotube transfer process. And at the time, this was, he felt, a convenient place. This is early in the morning and not quite compliant. So in fact, if you're dealing with synthetic nanostructures, maybe you don't have to be that clean in some cases. So ambient processing means doing it in the room. I think he probably needs safety goggles. Anyway, this is Max Schumacher a while ago. Max couldn't make the talk. Please tell him that I've honored him with his early picture. So this kind of on the edges of nanofab, I think, is very important. So we're now as a collection. We have a clean room that's smaller. We have an Exfab that didn't exist. We do MOCVD in the shared lab, and we've taken over the management of a lab that's more electronics prototyping. And remember, we're not the whole story. There's a whole bunch of distributed labs going on. So we have 600 users from 24 departments, 25 other schools, and 100 companies, large and small. And we don't do much characterization other than inline characterization. This is an older photo. We actually require the blue kind of lab coats in this part of Exfab. So if you look at it, we don't have a new building. We have a very old building, and we have managed to renovate pieces of it that were offices, right? We've taken service areas, and we've named them after beaches in California because it's a distributed lab. It's not all in one location. People have to go out in the hall, so it can't be that clean. We don't have HEPA filter coverage in these. We have little mini clean rooms, and we have this system prototyping facility. The staff have a big open seating area, and that's made a big difference. So you can see the green is class 100. Exfab might be 1,000 to 5,000. So quick run through of tools. The Heidelberg MA150 is a workhorse. It is used 24/7, so we're getting another one. Harvard has two. Why is it nice? No mass. And if you want something better than a micron, then you go and use the E-beam, and you still have no mass. So it's completely soft, and that's huge. This one's not so well known. This is a multi-protein patterning tool that has a Texas Instruments DLP inside and can resolve 1.5 microns. You can remove an cell growth layer and pattern where cells grow. And so that is a very useful tool. We do flip chip, but it's really flip wafer, pieces of wafer. There's a big project at SLAC on linear accelerators on a chip. And so these are done in a fine placer. We have 2 inkjet printers that are used heavily for printing different things at resolutions that are, again, not nano, but not exactly anything to sneeze at. For some people, that's perfectly fine. We do chemistry. We have fume hoods and a dual glove box, and someone like Zhenan Bao, who would be an organic electronics pioneer and major player, she has students using that because it's nice to have a lab that you can, that's open, that you can use for surge space or for doing things that would be not pushing the envelope, and a bunch of other things. We do our material transfer in the glove box, and we have polymer fabrication. And we bought one thing Stanford's been weak at, we haven't had the kinds of evaporators and sputtering tools that would be flexible and be able to deposit anything. The battery people are in there, they need some unusual things. They have lots of targets, and they are used very heavily, and we're getting more. So I guess the upshot of this I'll show in terms of our usage, but this last one, Boris Merman is a circuits designer, and basically he said, what if we had a shared circuits area, not for the undergrads and master's students, but for people who really otherwise would not know exactly how to interface with TSMC. You know, if you haven't done it before, if you're, you know, I've had students tape out, but always there's been an IC professor kind of hand-holding and making sure there wasn't some rookie mistake or screw up. And so Boris said, what if we have a facility that would be staffed by EE postdocs and SLAC, that national lab EEs. There's a lot of EEs up there, and they would help people to build things that might have to go into some robotic system, and so it's boards and flexible stuff. And it turned out that has worked out quite nicely. Some people need a lot of help, some people don't need help. The first customer, Stanford has a lot of quantitative psychology. It was a psychology prof that needed electronics. Okay, so you know, it's ubiquitous, and so that group didn't have a lot of EE internal know-how, and so they went for complete support. So one thing that I think is interesting with MIT.nano is all of these how-to process modules that we are not quite up on the web yet, but like you know, things like nickel silicide bonding. The Volterra is an odd kind of fountain pen tool, helpful hints for grayscale lithography. The staff didn't write these. These were written by graduate students in most cases. This is a quick guide to a line transfer of 2D materials in a glove box by one of Eric Pop's students. And shadow mask vendors. One thing that I think is underappreciated, and this is by Archana Kumar, who is a former PhD student. She now works at Applied Materials. On her own time, she has gathered all of the local shadow mask vendors. So the interface between MIT.nano and the whole Boston area, groups have unique knowledge. We're trying to get that in the open. So the real way to build all of this has been by teaching a course. We call these SOPs, or standard operating procedures or protocols. So Engineering 241 just wrapped up. Believe it or not, if you were at Stanford, it's finals week, okay? You know, I've petitioned the UN to ban finals in March as a violation of the Human Rights Convention, but Stanford, it's a quarter school, right? So be happy that you just finished midterms and that finals are at infinity in May. That's both faculty and students. Stanford loves the quarter system. So we had a 2-quarter course. That's the next best thing to a semester course, maybe even slightly better, where the student teams ended up proposing projects and negotiating with their advisors, with the staff, and sometimes external people, and with John and myself, to do something that's useful to the general community, useful to their own research. And we pull in some less experienced students. And so the outcome of that, and here's the cost, we had $70,000 that we got from the dean, because that's a lot of money. We have to pay user fees in the lab. We don't have a teaching lab at Stanford, and this wouldn't work in a teaching lab. We want the newest tools to be developed by the best students, and they get some credit for it. It isn't cheap, because that lab, we can't absorb that somehow. And by the way, Mary Tang, the SNF's managing director, is signing off because her staff's involved in every project. But we also roped in the local industry. And it turns out, whether large companies or small, there are people who know obscure things that can share them on using tools that may be out of our experience. So how is it working? Well, by affiliation, our usage is stable to up. The other would be mostly academics or national labs, mostly internal, as always. The interesting, with the standing up of Exfab, the use of the clean room appears to have dropped until you look at the multiple labs, which means people using both the clean room and Exfab would now be the majority. And so these tools are getting some traction. And I think the number of faculty groups is up to finally over 100 faculty groups. And what we would do in a future fab is somehow informed with this. You probably didn't notice the aerial view, but medicine and engineering are adjacent on Stanford's campus. The medical school is extremely interested in getting a new nano fab. And we would be interested in supporting that with them and the sciences. So we would probably be more bio-focused than MIT.nano. There is this SNSF. We have earthquakes in California and other issues that make the E-beam is in a special building with a special foundation. You know, MIT.nano has a fantastic foundation, and this new building does, and so the E-beam goes in there. There's also a flexible clean room that's yet another clean room. I look forward to touring the Media Lab's clean room that is apparently coming up. This lab does things like 3-inch lithium niobate wafers and all kinds of unusual processes. It was the Ginston Research Lab's clean room that's now moved over. Bruce Clemens in materials is in charge, and there's a bunch of staff in several buildings. So they have tools that would be like this Titan aberration-corrected TEM, FIBS, SEMS, mostly metrology, but not all metrology, and across the way from the SNF. So my students would have counts in both, that would use optical lithography in the SNF and go over into the SNSF. And by the way, there's a contest to name the future fab, and the letter S and the letter N cannot be used in the name because of tongue-twisting, too many Stanford Nano shared facilities. So how do we fund this? Each school is different. Cam Moeller in physics, now Dean of Research, and Philip Wong in EE, they started a nano committee in 2007 because they were tired of going to Berkeley to use the nano characterization tools. And they managed to get a budget. It's a fight every year, and it varies every year, to get tools acquired for shared facilities. And we sit around the table. I was co-chair for a while, and you have a bunch of deans. You think there's only one? No, there's the engineering dean, the science dean in humanities and sciences, the dean of research, the dean of medicine, the dean of earth sciences. They all sit around, and we attempt to extract investments that would be, into this pot of money, and then we go shopping. How do we buy things? Well, we instituted this survey process of getting to find out what the faculty need. That's a near-term thing. That's not really strategic, but it does get buy-in, and if it's transparent. So here's a page from an old survey. Who are you, and whether your faculty, staff, industry is included in the survey. And in a few years ago, we have departments from geophysics to biochemistry to pediatrics, radiology, surgery. It's a whole grab bag. And as you imagine, they don't necessarily all line up, but sometimes it's surprising how much cross department support. So Jen Dion in material science and engineering, Alex Dunn in chemi, Rod Ewing in geo, all of these different people get to vote on all of these different tools, and it's all kind of digested and balanced against strategic initiatives. So it is we bought 4 plasma etchers at once because there was a tremendous sense that we were short on plasma etchers. They were too old, got to get plasma etchers, and then ended up negotiating a better price by buying 4 at once. We were playing vendors off against each other and got a great deal. So in fact, I think MIT.nano, you have leverage, and it is a balance between things that would be bleeding edge and things that would be workhorse reliable tools. So in any event, I am looking at the time, I don't know if you want to see this except for, I'm going to skip a lot because I'm going way long and you can't, people are passing out and there's not enough oxygen in the room. But I'm going to skip through to an important paper. Well, I'll tell you this. This is an important paper in 1968. This was an important paper last summer. This is IBM Zurich work showing that the tunneling current between two metals separated by some organic molecules, you're getting in the current, if you do the second derivative, you're getting things that are related to various mechanical vibrational modes in the molecule. And boy, that would be neat. My thesis was a chemical sensor. It was nothing like this, right? This is like a spectroscopy, right? In fact, it's inelastic tunneling spectroscopy. This is wonderful, but you need to have liquid helium in order to get that kind of sharpness. So in fact, I've had a project since 2011 to do this electrochemically at room temperature, and the challenge is designing the interface and designing the electronics. The interface turns out to be 50 nanometers square, but the business end is a functionalized gold nanoparticle. And you're getting tunneling currents and attempting to pull out information. Let me just jump to how this was made. We decided to use an STM tip rather than a wafer for various reasons. Partly a postdoc that showed up, partly the fact that we didn't have any printers. And if we were going to functionalize on a single chip, we might as well functionalize on a tip. And so we actually started with a very non-planar substrate. It was actually platinum iridium STM wire, and then we made it even more non-planar by electrochemically etching it. This is the substrate. We then went to, and that's the SEM. Shuai Chang did the animation. We then deposited an insulator, ALD, and I put in, if you look closely, you can see the tips all around this puck. That went into the ALD in the SNF. Okay, that is a non-traditional fab, and we needed to do that. And there was a protocol to verify cleanliness for the puck and the loading procedure and everything else. So, in fact, how do you pattern on that? Spinning is probably not a good idea. Focused ion beam isn't quite that magical, but in fact, in practice, you can punch a hole on the end of that, and you have your interconnect and the hole, and you can go do your functionalization. This is PowerPoint chemistry. Now, the last step is the best kind, is PowerPoint chemistry. And so in fact, we were going to mount this in PDMS as an insulator so that there was only the tip exposed, and we're going to pull it through backwards. And so we put a microscope here, but this takes good hands. This is a manual thing. So what do? Well, I don't know about MIT, but at Stanford, you find people that are really smart, really good hands, and no coffee. Now, they aren't MIT undergrads, but they're probably in the local high school. So I recruited high school students to do this, and they are now at various other places at UCLA and Purdue as undergrads. But in any event, that was no mean feat. Then it goes into an electrochemical cell, and we worked on the electronics, and the circuit is just a potentiostat with one minor difference. It's massively lower noise. So there was huge efforts in the signal processing, the data analytics to pull this information out at room temperature. And Boris Merman, who's pictured, is one of the great analog circuit designers on the planet, analog digital. And so this is a $10,000 Gamry, and this is our little circuit. So we could start a company in potentiometers, but actually there were other things detecting that you could see these sort of peaks from leucine and deuterated leucine. If you can tell these amino acids apart with a single deuterium substitution, maybe we can do the kinds of inelastic tunneling like spectroscopy and do label-free detection. So we got a company going, and there are the founders. This is the usual fault line brewing company is walking distance from our place. Emmanuel's PhD from France, Chaitanya Gupta, yours truly. We have some values. I'm just clicking through this, and we have been going for some time and have raised a significant amount of non-venture money. And what are we working on? We were funded by DARPA and are continuing to be funded by DARPA for sepsis, for cytokine panels. But in fact, there's a lot of people, and this is Probius work, and in fact, Probius has used TIPS. Obviously, we're migrating to real lithographic nanotechnology and wafer scale fab, but people like peanut allergen and salmonella staph, and this is associated with E. coli. We've had a lot of work that would be in a paper in a conference in Toronto of the food safety people showing that we can do very nice assays of nasty things. So in conclusion, I think the build it and they will come is kind of out of that baseball movie, right? Of what was the name of it? Building it, and then the old ball players come from the earlier era. In this case, I think this is going to be a very busy place, because that space in a new clean room is among the most valuable commodities in any university, because it can be if there's an initiative in an area, you can do it. And if there's an initiative in another area, you've got the space to do it. So to my ability to advise Vladimir, Dennis, and all is very limited. But I guess at the MIT and over here, you have at the dawn of the Nano Age. Okay, I wanted to hit that over here, right? And are we at the dawn of the Nano Age? Well, I think we are, because it's not an age just to have a few, when do you transition from one age to another? You have to have traction, you have to have applications, you have to have real technology, and I think this lab might be the place where quantum and other new computing architectures are developed. You're set up and ready to go. I think to get this show on the road, the strategic investments, I noticed a new faculty member whose tools are temporarily on the 5th floor. Professor Nuri will have some of her tools in the fab. That is exactly the right idea. MIT.nano is going to attract everyone. I saw the cryo-EM. We call them Nobel Prize machines in the basement. You may want one, and you can go, if you're in the bio side, these are incredibly difficult, expensive, and to have them in the building is important. I like, that prototyping was done in the FIB. The FIB is used a lot as a fab tool, not just an analytical tool, and that may it may change what kind of FIB you want. And I think there's an opportunity to launch a course that would bring in students from engineering and science and get them busy getting credit developing new processes, documenting them. Now, you need money for new tools, but actually the old ones are pretty good. This is a tool that's older than most of the people in the room. We just got rid of it last week, and I took this picture outside the clean room. There's a page on its history. This was made in Wilmington, Massachusetts in the 1980s and shipped out to California. The Plasma Quest I thought was from Japan, but it's a US tool that I think had Japanese investment or something. I don't know what the history is, but it's finally gone away. It was a very contentious etcher before we got our new Oxford etcher because it switched from fluorine to chlorine. And the fluorine and chlorine people were almost coming to blows on the number of days in the week. It was chlorine and fluorine. We got a new etcher, problem solved. So sometimes you can pacify the restless nano grad students. I think the coordination between MIT.nano and a lot of other fabs, that would include this interesting one, Skywater in Minnesota, the local one, and Albany Nanotech. What do I mean by tool mapping? I tried this at Stanford with a foundry to indicate the tools and processes that easily transferred to the foundry. The foundry wouldn't tell us what the tool was or what the process was. They just had a green, a yellow, and a red dot on a process. If it was green, it was easy. And if it was red, it wasn't. There's a lot of small companies involved and grad students who might want to commercialize it. Knowing that you're on the green tools would mean that you could move quickly. And you could actually do that for multiple foundries. I think that might be an accelerator. And MIT faculty are going to be developing new tools. They might be interested in putting them in the lab, and I made this up before talking to the management today, and that's actually planned. We have a deal where if there's a new vendor or a new tool from a vendor, we'll try to find space, put it in the fab. They don't have to, we don't buy it, they don't give it to us, they keep title, and we'll see what the usage is. You know, you experiment, and then if it's 6 months, no one's interested, take it out. So I think that kind of dynamic thing as MIT.nano spools up. And these in and out users that may not do their whole PhD in MIT.nano, but MIT.nano is critical to the PhD. So they're in for a few steps, they go to the private lab, they're back. These people are super important, and their fabrication needs may migrate into MIT.nano. And lastly, the number one priority for our future fab is affordability for the faculty. And that is something where the institution can help, and Stanford recognizes our fabs have been too expensive, and we're trying to make them cheaper, but in the future, they will become a lot cheaper. How does that happen? You pile up giant amounts of money. It's called the endowment, and you hope you can invest it and get a return, and you use that return to pay salaries and buy stuff, and then you offload it becomes not a full user facility, it's subsidized. And that's a word that we are partially subsidized, and that will increase in the future. Lastly, this is the Stanford golf course. There's a cafe up there, and we went up there actually almost 3 years ago, and you can see there's a mixture of SNF and SNF staff. And Mary would be the managing director, who's done a fantastic job. So acknowledgments, I have a bunch of people, including the high schoolers that helped on that unusual fab, but I will, and the people that funded it at DARPA, but I'll really emphasize Larry Goldberg is one of these people in Washington who has defended the investments in infrastructure in nano. And that isn't easy in the NSF, and he's been at it for a number of years and has been very successful. Will there be a successor in 2024 that MIT might compete for, right? The successor to NNCI? If it happens, Larry will be one that has continued to fight for it. So I am over time by a lot, but I hope you found some of this interesting, and I put together things, given the fact that I'm the first in this series, it's only up from here. You have Paul Alivisatos, you have Eli Yablanovich, okay, you may have heard of him, and you have Don Eigler, right? Ex-IBM Almanen atomic guy, and then there's this local guy, Bob Langer, right? and so you can see I've set that, and so you can do this sort of exponential plot. And thank you very much for your attention, and I'm open for questions. Yeah, I'll leave that open in case.
Well, thank you for giving us a great start.
So, it's basically you have, I was here at the dedication of MIT.nano, and it was it's an awe-inspiring thing to pull off this investment. And it is it's now going to be, it's like the boundaries of the painting, right? You have the frame and the canvas, but what is going to get painted on it is something that is a lot of possibilities. And that's, in a place where we have no space and we don't have the ceilings for the tall tools, right? That's another issue, right? So there's some envy of where you are. And we hope to one-up you in about 5 years.
Well, we also look forward to sharing. So
yeah,
please,
well,
send your students this way.
I think we'll be more bio-flavored than MIT because your bio is so already has such fantastic facilities in your institutes, so you don't need as much. But anyway, if you have any questions, I'm happy to.
If there are any questions, please.
You mentioned the student revolt through the overuse of by local small companies. How did you solve that? But you still have companies there. I mean,
we didn't throw
that overall question.
We did not throw the companies out because the NSF is not happy to get an email from, and some of these companies weren't small. Intel was one of the major users. Why would Intel use an academic lab? It's because we have a lot more flexibility, and they would be able to do things quickly and inexpensively. We charge them more, of course, but they're very happy to pay it. Well, the answer would be priority reservations. That the companies would be, in some cases, their processes were stretched out. Because depending on the crunch tools, we identified what the real problem tools were, and we actually had kind of a reset where we did a lot of preventative maintenance on the tools. We just said stop. So they basically, I wasn't Yoshio was in charge at the time, but with that many students showing up, this is the user community, there was a response. And the companies, in some cases, there were problem individuals that were cutting corners because they're in a company and it's not their lab, and maybe who cares, Stanford's rich, which it's not really, as MIT is not really rich. We're very heavily invested, and so there was a cultural change. There was retraining of people, and we got through that. And of course, soon thereafter, the economy went soft, and that made sort of took some of the industry usage away. But notice you have 40,000 square feet. How many?
Of clean room.
Of clean room.
If you had it all up, there's about 100,000
okay, 40,000 square
feet.
feet. Okay, you should measure it in like hectacres, the SI unit, or the metric unit. In our case, we have 9,000 square feet of clean room, and these ancillary spaces would add in a few thousand more. So it's very tight. And I was giving a tour to our newly admitted grad students, who probably had a tour of MIT.nano. And I said, well, this is a place where you can do good work. Ask Professor Schulacher at MIT when you visit. There's still good work to be done here, and we are working hard to get something new, but it's not going to be done by the time they get their PhD, or just at 5 years out. So anyway, it's a management challenge because it's an open kitchen, and people are cooking different cuisine. Blas Cabrera, I could ruin his science experiment, right, by becoming too loose. But there are other faculty in the other ear saying this lab is rooted in the 20th century MOS technology, and we need to embrace additional materials. And so we have crept very carefully in that direction. And we have duplicate tools in some cases, so there's various levels of contamination. It's manageable. But I think we have several faculty have banded together and have a lab that would have its own tool set under much tighter restriction. Once one of my students got permission to use an ALD that was pristine, and it made a huge difference in his PhD to get that really good hafnia that we couldn't get in the SNF because the tool has been used for too many things. So Hank, you had that dedicated lab, and without it, if you were folded into MTL, nanostructures progress would have happened, but in a there may have been student disruptions and faculty disruptions. So I'm not saying the shared lab isn't everything, but to keep a flux of new things in, a lot of what you were working in is now mainstream, right? Yeah, and so I think you have to have a thick skin to be in charge of these facilities, right? That Professor Bulovich gets delegations from people all the time, I'm sure, saying.
It's fun.
Yeah.
It's definitely fun. Other questions?
Yeah. So, yeah. Okay.
Oh, yes.
Hi.
Mark.
So I'm just interested in this sort of 6-month trial thing with
Yeah.
the company just sort of loaning you the tool. I assume you had to have some preparation because I think there's going to be 6 months is not long enough to get people to be interested in new tools. So how did you deal with that?
Well, we would have a fairly good effort to promote that to the faculty, the postdocs, and the senior grad students. Like the company comes in and gives a seminar, and these can be packed seminars. And the tool is obviously, it's not just any old tool. There's a clear indication it might be a big win, and maybe add something that is unique in that national network that we're part of. You know, if we can add something new, we can say to NSF, hey, we can process, you know, we'll then advertise that we could have wafers FedEx from anywhere, right, to use it. So the company, like the visibility of MIT.nano, there is a spin-off out of MIT. It's Exfab, right? The new spin-off of Parker Gould and Mitchell Shing. Our recent PhDs, or not quite PhDs, they have a radical new concept of a lab that's only $1 million instead of $100 million. It's a smaller fab with small wafers, and this is something that if they had a package or pieces of that fit MIT, it's an MIT spinoff. They should get a red carpet. That's our color, right? You have this anyway. So some sort of like, gee, wouldn't it be great if that company was a success? Is important because we need new companies in fab. But if it was actually a PhD accelerator at MIT, wouldn't that be cool? Right? And so I think that you have the space to be much more aggressive than we do. We had to take out these old etchers that are still working, and people are reluctant to let them go because they work, right? And the recipe is known, and people are uncomfortable. It's like a chef losing a special oven because it's 200 years old and it's expensive, and then they take it away, and there's emotional withdrawal from a plasma etcher. So if you haven't been there, and some of you may be in the middle of this, you would definitely, that would resonate. People panic, right? When you think you're going to lose a capability. So we have to prove that we have something that's a drop-in replacement for that. But I think things are changing fast enough, thanks to the push of the whole nanotechnology effort. It hasn't quite penetrated. The one lab, for instance, would be a flavor of nanotechnology that's semi-shared outside, right? Yeah. The main MIT.nano, and Professor Nuri's work would be even maybe further out. But to get the first tools here that are only accessible to the best students, right? The ones with good hands that don't bust stuff, because if you break it, it's not really a commercial tool, right? To get these alpha versions, not the beta versions, is a competitive advantage for the institution with the guts and resources and space to do it. So you have things coming out of MIT that everyone else is racing to catch up with.
Well,
yeah,
thank you very much.
Which is the situation normal for the last 170 years or so. But anyway, speaking from the West Coast, yes.
Did you have to do anything in particular to attract companies to use it? I know that you're sort of in the epicenter there.
Well, I think the NSF has helped make it more visible, because people probably would think it's, hey, Stanford's private, it's not open. Berkeley is less open than we are, even though it's a state school. But there's a way for companies to get in through writing a check to a program that funds the lab. In our case, we can't do that. We just charge user fees. And we charge twice what the academic fees. MIT would be charged the same as I would be. And the companies get 2x in our facility for reasons that are lost in the mist of time. Our sister lab, in some cases, charges 3x. And to throttle usage, some of those schools have gone up to 5x on industry because they have the deep pockets and they'll just take over. And is that a problem? Well, actually, the industry ultimately will cut back, right, and maybe get their own tool, but the university can benefit from that revenue stream. So I was impressed that Mass General has put a new tool instrument in the basement, right?
Yeah.
That is, exactly the kind of thing where you're engaging that relationship with Mass General. How is that going to evolve? And now there are people here using it. There's MIT people using an instrument that MIT didn't buy. And so, is that good? I think that's a good thing, right? To have this lab where it's open in that way.
Well,
yeah.
I will at this point have to thank you tremendously
because
for.
no,
it's we can keep on going.
Well, there is a reception, and I'm happy to continue to discuss things. It is the culture of each school. This isn't Harvard, right? This isn't Stanford. This is MIT, right? And so the MIT.nano thing that builds up, that works here, will be different, and we might learn some things for our future fab.
Indeed, the goal is indeed to engage across the disciplines, and you have presented us a very wide way of thinking about how to approach that. Before we conclude, a couple of things. One, there is a reception on the 3rd floor of MIT.nano in front of the boardroom. There'll be some nice snacks. Please join us. Professor Howe will be available through about 5 p.m. Now, beyond that, before we do conclude, I do want to offer you this one gift. This is a little token to you for being the inaugural speaker of this series. It's your very own piece of MIT.nano. It's we took a whole section of the building down just to make this one for you.
Okay.
But it is the original limestone, 400 million years in the making. It took us a little while to place the order.
From which river in China? No, it is, right?
It's from the Yangtze Plateau.
Yangtze Plateau, okay,
Yes.
and where they have this unusual rock that looks like wood, right?
And we have carved it with MIT.nano logo just to make sure you don't forget. But thank you so much for coming here.
Appreciate that, and we'll put it in my display of interesting. I have a little museum that's about that big of nanotechnology, and this would be fit right next to that. So, thank you.
Thank you for being here.
Thank you very much.